Okay, today's class is very important because I'm gonna talk about a couple of fundamental concepts in dynamics. Some of you who come from computer science background or who have not taken a dynamics course, this material will be very useful and important. No matter what the object is, whether it's a spacecraft, aircraft, or UAV or UFO, you can use the same techniques, same equations to derive differential equations of motion and understand its dynamics. Towards the end of this lesson, I'm also going to talk about a very important concept, which is called as quaternion. So in today's class, I clearly can't do animations or I cannot show you movies. So I'm going to give you all the theoretical background, and then I will give you the link onto YouTube animations. They will actually animate the quaternions. That will give you a geometric perspective. So that you understand what do those means, what do those vectors mean, and what those vectors, how do those work in something called as the hyperplane. But I will try to give you the physical interpretation. I will also give you the mathematical understanding. And most importantly, I will show you if you have to use quaternion, how you can implement that in a computer code. That is how it is used. In next class, so I already uploaded the next project. So in the first project, we have created this aircraft model, and wherein you supply 12 states and time, and then you can see the aircraft. In the last class, I showed you actually what happens when you have a gimbal lock. Please understand that gimbal lock occurs because we are using something called as Euler angles. If we migrate our formulation to quaternions, the gimbal lock will not happen. And it's actually amazing to see when you use quaternions, how the math works out and that the problem of gimbal lock disappears. So in next class, what we are going to do is we are going to take this animation and then we are going to integrate that animation to the differential equations of motion of the aircraft, which means we will have the aircraft, will supply some artificial inertia values, will supply some trajectory, and then we will perform the numerical integration in the Simulink, and those 12 states will be fed to the animation, and you will actually see your aircraft flying as per the dynamical equation of motion. And then we will, as next chapter is on forces and moments, so we will integrate aerodynamic forces, wind model. We will also look at the airfoil characteristics, etc., and will increase the fidelity of simulation. And then we will look at trimming, path planning, etc. In today's class, we are going to focus on, again, kinematics and dynamics. And this topic is very, very important because the equations that we derive at the end of this lesson, they provide the output to the animation what we have created. So in the last class, we briefly talked about different states. Now, please try to understand, to describe the aircraft position, velocity, and attitude orientation, we have 12 states. First 3 states is the position of the aircraft with respect to the fixed inertial frame. And a quick recap. Can someone tell me what is the first frame that we start with? If you want to describe the aircraft motion, the first frame, inertial frame. Second frame, vehicle frame. After vehicle, so the inertial frame and vehicle frame, they are related by pure translation, which means Pn, Pe, and Pd gives you the relationship between the earth center, earth fixed frame, and the aircraft centered CG vehicle frame. After the vehicle frame, what do we have? Vehicle 1 frame. And how do we get to vehicle 1 frame? Rotation about Z axis. Then we go to the vehicle 2 frame, and that is achieved by the rotation about Y axis. So we have the pitch rotation. And last frame, vehicle 2 to body frame, is achieved using roll. Once again, inertial frame, vehicle frame. In vehicle frame, vehicle 1 frame, which is yaw. Then we have a pitch, which is vehicle 2 frame, and then we have roll. Now we are in the body frame. And body frame is the frame that is attached to the aircraft body. U, V, and W, those are the velocities of the aircraft expressed in the body frame. So those are the velocities in body frame. P, Q, R, those are the angular velocities in the body frame. So you have P, which is the angular roll, Q, angular pitch, and R is angular yaw. However, when we go from vehicle to vehicle 1, vehicle 1 to vehicle 2, vehicle 2 to body, that is where we have those inertial angles, which is heading angle, which is yaw, then we have pitch, and then we have roll. So those are the different frames. At the end, once we get to the body frame, after body frame, please try to understand, we have, even though aircraft is going in certain direction, the air might be coming at a different angle. The orientation would be different. So the aircraft, the velocity of the air, which is impinging on the aircraft, will be at certain angle. So what we do is, from the body frame, we go to stability frame, and in the stability frame, the angle of attack transformation is performed, and then we perform the side slip angle. So now we get to the wind frame. So those are all the frames that we look at when we study the aircraft dynamics and aircraft motion. At the end, what we need to do is dollars to dollars, pesos to pesos, forces, movements, and all the vectors, positions, velocities must be expressed in one consistent frame. You cannot have force in the body frame and velocity in the inertial frame. Both of them should be in the same frame. And that's why we have these rotation transformations. So we looked at the translational dynamics. At translational dynamics, we have Pn, Pe, Pd, which are, and we take the derivative of it. So we get the velocities. Those velocities can be transferred to the body frame by using the rotation transformation. And please understand, on the left hand side, what you have is you have Pn dot, Pe dot, and Pd dot. And on the right hand side, you have the velocities that are in the body frame. And this transformation is nothing but, this contains the transformation that takes you from vehicle to vehicle 1, vehicle 1 to vehicle 2, vehicle 2 to body, and now you have the velocities in the body frame. So you have 3 rotations that are combined in that rotation transformation matrix. And so here is something that I want to sort of give you an idea, is imagine U, V, and W. Those velocities that are in the body frame are measured by the accelerometer or integrating the accelerations once. So U, V, W come from sensors. And then what you do is you perform this multiplication, and you have the derivatives Pn dot, Pe dot, and Pd dot. So you get sort of Pn dot, Pe dot, and Pd dot, and you integrate those once, and you have Pn, Pe, and Pd. From the GPS, if the aircraft has a GPS, GPS is gonna give the flight computer Pn, Pe, and Pd. So right now, what you have is you have a GPS provided Pn, Pe, Pd, and you have flight computer computed Pn, Pe, and Pd. So basically, what you do is you can perform a simple least square filtering and get sort of an optimal solution. And you can basically make this process even a little bit more sophisticated by taking into account the variances, covariances, and implement some sort of sophisticated filtering technique like Kalman filtering. Now let's talk about the rotational kinematics. The rotational kinematics equation is if you have the body angular velocity, and those body angular velocities are related to the inertial velocities, which is nothing but the roll velocity, which is p dot. Then you have the pitch velocity, theta dot, and you have the yaw velocity, which is yaw dot. So, I mean, psi dot. So basically you have roll, pitch, and yaw derivatives. Those are related to P, Q, R. Please understand, P, Q, and R, those are the aircraft body angular velocities that are measured by the strap down inertial measurement unit, 3-axis gyroscope. So you are getting that measurement, and then with this transformation matrix, you can, so basically what you have is you get this from your IMU, inertial measurement unit, 3-axis accelerometer, 3-axis gyroscope. So gyro 1, gyro 2, gyro 3 give you this reading. You compute this matrix, and then you get roll, pitch, and your velocities, and you subsequently integrate those, and you get something called as attitude angles. So those are also called as inertial angles. So at the end, these are the 6 kinematics equations, and these equations give you the complete aircraft kinematics, which means it gives you aircraft positions X, position Y, position Z, orientation about X, orientation about Y, orientation about Z. And the way it works is you have this IMU, inertial measurement unit, 3-axis accelerometer, 3-axis gyroscope, and you get UVW and PQR, and you perform the integration and then find the solution for Pn dot, Pe dot, Pe dot, and Phi dot, Psi dot, and theta dot. And these are called as kinematic equations for the aircraft. No matter what type of object it is, whether it's a UFO, UAV, quadcopter, hexacopter, octocopter, these equations are going to remain the same. So as long as you have a flying object, the kinematic equations are these. Question? Yeah.
What side is the inertia depending on the
There is no inertia what?
on the fourth slide, so
On the fourth slide, okay.
the rotational kinematics, I see I on the first rotational frame, but is there?
Oh, I is an identity matrix.
Oh, identity.
And the reason I wrote this identity matrix is because if you remember, if you were in my robotics 1, remember I wrote this equation for robotics 1, omega x, omega y, omega z, the frame rotation, first rotation matrix, frame rotation, second rotation matrix, frame rotation, third rotation matrix. So which is completely analogous to the way we derived the Jacobian in robotics 1. So this I is not an inertia matrix. Kinematics does not include inertia, no mass, no forces. Kinematics only deals with force, moment, the velocities and accelerations and positions. So these are the kinematic equations of motion. Now, please understand, when we solve these equations, you would first solve the rotational velocity equations, and at every step, you will get the output of this equation, plug that in the top equation, and then find out the solution. And so this, if you think about it, these 6 equations can be solved simultaneously, but you need to solve the last 3 equations first in that block, capture the data, solve the next set of equations, and recursively you have to go back and forth. We will do this on Thursday. So basically we are going to take kinematic equations, we are going to take dynamic equations, we are going to numerically integrate those and feed the solutions to our animation. Everyone understood this? Any question on kinematics? Okay. This part is super important. In last class, I talked about the derivative of vector. So derivative, when you take the derivative of vector, you have to take the derivative of the magnitude and you have to take the derivative of the vector, unit vector itself. So in the last class, I actually derived the whole mathematics of it. But at the end, what I want you to understand is if you have a vector, vector is going to have a scalar quantity or a magnitude, and then it's going to have the direction. So this is the magnitude, this is the unit vector, so this is the direction. When you take the derivative of vector, you have to take the derivative of magnitude and also you have to take the derivative of direction. If the direction is constant, if the direction is not changing, then clearly this value is 0. But in general, when you have an aerial robot, your magnitude is changing and also your direction is also changing. Everyone understood this? And that's why we derived this expression. If you want to take the cross products of vectors, remember circle of vectors, I cross j is k, j cross k is I, k cross I is j. So you have to follow the circle of vectors. And then in the last class, I derived the expression for a three-dimensional rotation. Everyone remembers that? Any question? That is a very, very important equation. And especially if you have not taken any advanced course in dynamics, this might be a little bit difficult to grasp in the very first go. But what it means is at the end of the day, remember this, you have the frame angular velocity. This is the angular velocity of the frame. And this frame has x, y, and z. So I, j, and k. This angular velocity vector could be the rotation about I, rotation about j, rotation about k. What we need to do is we need to take the cross product with respect to vector. And that gives me the time derivative of this vector. So if I were to say dv by dt, then what I do is I have this angular velocity and then I have this vector. Now I need to be super careful here. This omega, if I were to write this down, this is omega x I plus omega y j plus omega z k. So omega x is the angular velocity about x-axis, omega y is the angular velocity about y-axis, and omega z is the angular velocity about z-axis. And what I need to do is I need to cross it with the vector. And this vector could have three components. This vector could be something like, if I were to write this, xi plus yj plus zk. And this vector can be anything. This vector can be a position vector. This could be a position. This could be a velocity vector, or this could be an angular momentum vector. So no matter what the vector is, if you want to take the derivative of the vector, it's always the cross product between omega. So I need to write this down. I'll show it over here, which is dv by dt is equal to omega cross v. and omega is a vector and v is also a vector. Again, v could be a velocity, v could be a position, v could be a displacement, v could be a force, v could be an angular momentum, or v could be a linear momentum. So what I'm saying is it's in general representation of a vector. Everyone understood this? This is very, very important. Now, what I'm going to do is I'm going to look at Newton's law. We are going to apply Newton's law in a translational coordinate frame and Newton's law in the rotational coordinate frame. Conventionally, Newton's law is written as force is equal to mass times acceleration. Okay, Newton's law is written as force is equal to mass times acceleration. Okay, do you know Redkar's corollary to Newton's second law? If you are in robotics one, I already told you, but do you know the Redkar's corollary to the Newton's second law? Force is equal to mass times acceleration. Okay, so to cause, let me crack this joke and then I will answer your question. So, okay, so force is equal to mass times acceleration, which means to generate acceleration, you need force. Do you agree with me? Sometimes, so Redkar's corollary to that law is sometimes force alone is not enough. Sometimes force alone is not enough. And what you need is you need a jerk to get things moving. So sometimes when the things are difficult, you have to be a jerk to get things moving. How do I represent this mathematically? I take the derivative of force is equal to mass is a scalar quantity. So no derivative. Derivative of acceleration. What is the derivative of acceleration? Sure. And what is the derivative of force? Impulse. So which means many a times if a nut or bolt is stuck, what you do is you take a hammer and hit it. So you give it a jerk and then basically the things get moving. Okay, there was a question. What was the question? Yes.
Professor, you said like that vector v could be anything. So can it be omega?
Yes, you can do omega cross omega. Absolutely. Or you can do j, actually we will talk about it. We are going to take the cross product of omega cross j times omega. So I'll discuss that. It can be omega as well.
Okay, yeah, thank you.
Okay, so now Newton's second law, if you look at the strict definition of Newton's second law deals with momentum. It could be a linear momentum or it could be angular momentum. What is a linear momentum? Linear momentum is mass times velocity. Rate of change of linear momentum is equal to force. That is what is the Newton's law. Rate of change of linear momentum is equal to force. But since mass is constant, we take the mass outside that expression and we can say that the rate, so mass is constant and we have the rate of change of velocity is equal to force. Rate of change of velocity can be equated as acceleration, and now we have force is equal to mass times acceleration. But please understand, when you have sort of a rocket and the mass of the rocket because of the fuel consumption is changing, or if you have an aircraft and maybe the fuel gets burned. So if you want to apply Newton's law, you cannot assume mass to be a constant, and you need to take that as a quantity and take the derivative of the linear momentum to equate that to force. But in the case of the simple kinematics and dynamics and simple aircraft dynamics, we assume the mass is constant and we actually take it outside and we have the derivative of Vg. Now, let's try to understand one important part here is if I want to dissect this vector, Vg is the velocity of the aircraft. Vg is a vector. So it has some components in I direction, some component in J direction, and some component in K direction. And if I want to take the derivative of vector, I have, it's very important, derivative of magnitude, and then I have derivative of direction. Everyone understood this? So this is exactly same as you have P is equal to P I, and then if I want to do it something like this, P dot, this is going to be P dot I plus P I dot, which is P dot I plus P I dot is nothing but P, since I'm taking the magnitude outside, P here, omega cross I. Are you with me so far? So this, if you look at this equation, Vg is a vector. So this is the derivative of magnitude of the vector. And this indicates the change in the orientation, or basically the change in the direction, or I would say derivative of direction. Are you with me so far? This is a very, very important equation. So now what I'm going to do is I'm going to substitute this quantity over here. So as you can see, I have this mass. This m, small m, indicates it's a scalar quantity. It's not a vector. Mass is scalar. It does not have direction. Mass only has magnitude. Multiplied by this derivative of vector is equal to external forces. Everyone understood this? That is how we will apply Newton's law in the case of an aircraft. At the end, I'm not going to ask you to derive these equations. As a matter of fact, I'm not going to ask you to solve these equations by hand. What we are going to do is, once we understand what these terms are, what these cross products are, then we are going to write a MATLAB code that will numerically integrate these equations. So this is again same as previous one, but now next part is what I want to show you is if I want to express this expression, which is mass times the rate of change of velocity is equal to force into the body frame. These are the forces, angular velocities, and the velocities in the body frame. And I'll explain this again step by step. So this equation is a form of force is equal to mass times acceleration. Force is equal to mass times acceleration. And what I want to do is I want to express this entire equation in the body frame of the aircraft. Body frame. And why do I want to express this in the body frame? Because please understand the U's, V's and W's. U is the body velocity in X direction. V is the body velocity in Y direction. And W is the body velocity in Z direction. So U, V, W are the body velocities. So these are the body velocities. PQR are the body angular velocities. So body angular velocities. And Fx, Fy, Fz are the forces in the body frame. So these are the forces. And what I want to do is, before even I go to this expression, I want you to understand sort of the physical interpretation of this. Please note, this is a vector quantity. This is also a vector quantity. And this is also a vector quantity. There are two ways you can write a vector. So for an example, I can write this vector VBG as, since U is in the I direction, U times I body plus V times J body plus W times K body. So IB, JB and KB are the unit vectors in the body coordinate frame. Everyone understood this? I can also write omega B as P IB plus Q JB plus R KB. So what this represent is, I have this aircraft. I have done all these transformations, and you will realize why I'm very particular about this, because what you want to do is you want to perform a cross product of two vectors. So you have, this is my I, this is my J, and this is my K. This is I body, J body, and K body. And what I have here is, I have, this is my U, this is my V, this is my W, and PQR are the positive rotations about these. So this is P, this is Q, and this is R. Everyone understood this? It is extremely important to note that U, V, and W and P, Q, and R are expressed with respect to IB, JB, and KB. Before you substitute any of these quantities, vector quantities, into the equation, you have to make sure that all the angular velocities, all the translational velocities, and all the forces are in the same coordinate frame, and they are following the same right-hand convention. Everyone understood this? Okay. Now, what I want to do is, I want to perform this substitution. So this substitution is, and I will show you this substitution here. This substitution, I can express, instead of I, J, and K, instead of expressing that as a row vector, I can express that as a column vector. So U, V, W, P, Q, R, and X, Y, and Z. Now, there are two ways to substitute. First thing, if you want to substitute, what you can do is, you can write this equation something like this. M, and this guy, dV by dTB, is going to be something like U dot IB plus V dot JB plus W dot KB plus WB. So this guy is PIB plus QJB plus RKB multiplied by, so now you have a cross product multiplied by this vector, which is nothing but, please understand, UIB plus VJB plus WKB is equal to f of x IB plus f of y JB plus f of z KB. Are you with me so far? So what I did is I took the derivative of magnitudes, substituted that in the first term. Then I took the angular velocities, substituted in the second term. I have a cross product and I have the terms on the right hand side. Please understand, these are vector equations. One vector equation means three scalar equations. Why? Because you have to collect all the I, all the expression in IB, all the expression in JB, and all the expression in KB. Everyone understood this? So yeah,
Wouldn't the derivation of vector VG with respect to B should be like it would have two components for each, right? The derivation of magnitude like chain product.
so that's exactly what this is. This is the derivative of magnitude, and this guy cross product is the derivative or change in the direction. So let me take a step back. This vector magnitude, magnitude, derivative of magnitude, derivative of direction. So derivative of magnitude is v dot vg dot, and this guy is nothing but omega. Instead of taking p here, the p is inside. So this is written something like this. Does it make sense? So this is how you can write this down. Alternatively, what you can do is, if you want to express directly the cross product, you can actually do a cross product for the column vectors. And let me tell you, the answer is going to be the same. The answer is going to be the same. So what you can do is, if you perform this calculation, and at the end collect the terms corresponding to IB, collect the terms corresponding to JB, and take the term corresponding to KB, you are gonna get this would be the expression for IB, this would be the expression for JB, and this would be the expression for KB. Everyone understood this? I can do that, but at the end of the day, you are gonna get the exact same equation. And believe it or not, I did something similar in my last class. So wherein I had a frame, wherein I had the rotation of the frame, and then there was a vector. So basically, once you perform this, you are gonna get one vector equation that will have three scalar components. One, if you collect all the i's, you are gonna get q dot is equal to rv minus qw plus 1 fx divided by m. If you take jb's together, you'll get v dot is equal to pq minus ru fy divided by m. And if you take kb terms, you'll get omega dot is equal to qu minus pv 1 fv divided by m. Everyone understood this? I believe that you must have seen similar type of math in physics 321, or at least in undergraduate dynamics or vector mechanics or vector calculus class. Before I proceed any further, any questions on this math? I want you to be absolutely clear. This big expression comes from the derivative of magnitude and derivative of direction. Next, you want me to derive this equation? Are everyone okay with this? one thing I will say that this expression. Okay, R is the angular velocity and V is the translational velocity. So R is the angular velocity and V is the translational velocity. Q is the angular velocity and W is the translational velocity. So these terms you are seeing here, they are the product. They are the product of angular velocity multiplied by translational velocity. Everyone understood this? But another important thing which I want to tell you, this is very important, just to give you some physical understanding to it. This is the product of angular velocity times linear velocity. This product equals u dot. And what is u dot? Which is the acceleration. Are you with me so far? These are the acceleration terms. So what exactly is happening? Think about it. When this is exactly the same thing that you have experienced as a kid. So imagine there is a merry-go-round, okay? And basically, as a small kid, we played on the merry-go-round. The merry-go-round is turning, and the child tries to go towards the center. So merry-go-round is turning. The child goes to travel towards the center. Please check this. Merry-go-round has an angular velocity. Do you agree with me? The child has a linear velocity. Now visualize you are that kid, you are that child, and you are trying to go forward. What would you feel? You would feel a sideways acceleration. And that sideways acceleration is because of the product of the linear velocity and the angular velocity. Now that is sometimes called as Coriolis acceleration. And this is something just on the side note. I don't know if you see the series The Simpsons, okay, there is an entire episode on this Coriolis acceleration. So it is said that if you are in northern hemisphere or if you are in southern hemisphere, basically if you flush the toilet bowl in northern hemisphere, the water flushes clockwise, and the southern hemisphere it flushes counterclockwise. Here is the reason why. Basically, this is the Earth, spherical Earth, and it is rotating like this. And what's going to happen is, see, the water, because of the gravitational acceleration, is going to go down, but Earth is rotating like this. So what's going to do is it's going to push the water flushing down is in the clockwise position. Now, if you look clockwise rotation, if you look at from the southern hemisphere, gravity is pulling that water up. So think about it, gravity is pulling up. So the vector, the velocity vector is like this, but Earth is still rotating in the same direction. So which means it is going to go in an opposite direction. That is, the water would flush in the northern hemisphere. There is an entire episode of The Simpsons on this concept. So remember this. Okay, everyone understood this? At least watch The Simpsons. Okay, now this sets the stage for more. Yeah.
So that's actually true, isn't it? Is that actually true, or is it just fake?
Well, Coriolis effects are true because that is how the gyroscope, the MEMS gyroscope work. But what they showed is more like a myth because the velocity is so small, you won't be able to see it. However, if you look at the river patterns, for example, there is a river, Ganges in India. If you look at that river is supposed to go straight, but because of the Earth rotation, you will see the river direction is skewed clockwise. So when you have significant velocity over larger distances, you will see the effect. The other thing you will see the effect is when you are firing an intercontinental ballistic missiles, ICBM, even though you are trying to hit the target here, you are gonna hit over here. Because of the Earth rotation, that missile will go and hit the target. But that happens on ICBMs, not the usual. I mean, those effects need to be predominant to see actually you would be able to measure those. Okay. Now here comes the kicker. This is the Newton's second law in the rotational coordinates. So Newton's laws is rate of change of linear momentum is equal to force. Similarly, rate of change of angular momentum is equal to torque. However, there is a caveat. This equation is only valid when you apply that about the center of gravity. This equation is not valid if it is at some random location. So rate of change of linear momentum is equal to force. Rate of change of angular momentum is equal to torque. Everyone understood this? But if someone asks, so remember the equation that we used to seeing T is equal to I alpha. This equation is only valid when you apply that at CG, when you apply that at the fixed point, or when the velocity of that point is perpendicular to the angular motion. So which means the cross product is 0. So V cross omega is equal to 0. So remember, T is equal to I alpha is not valid everywhere. On the other hand, force is equal to mass times acceleration is valid anywhere. And the reason for that is, please try to understand, torque is about an axis. Torque is about an axis. So wherever you assume that axis, the magnitude of torque and magnitude of I would change. But that doesn't happen in the case of force is equal to mass times acceleration. So remember this, T is equal to I times alpha, this equation, and its equivalent form, rate of change of angular momentum is equal to torque, is applicable about fixed point, about CG, and when omega cross W, omega multiplied cross W is 0. Yeah, question.
Is CG?
CG is the CG of the aircraft. So that is where you can balance the aircraft. So C, center of gravity. So CG. Okay. Any other question? Okay. Now, please understand, just like the linear momentum is mass multiplied by velocity. Angular momentum is mass moment of inertia multiplied by angular velocity. That is also a vector. So what's going to happen is, here we have to take the derivative of vector. Whenever we have to take the derivative of vector, we have to take the derivative of magnitude, and then we have to take the derivative of direction. Are you with me so far? So derivative of magnitude is this guy. Derivative of magnitude is this guy. And derivative of direction is this guy. Are you with me so far? So omega cross HB, which is same as this guy. But here, instead of P, I have H. And H also has a magnitude and it also has a direction. So I have this quantity. And then I'm going to substitute the values for mass moment of inertia. What is mass moment of inertia? Mass moment of inertia is mass multiplied by the radius of gyration square. So for an example, if you have a rectangular object, and we studied this in robotics 1. So if you have a rectangular object and you consider its principal axis, you can find out the mass moment of inertia about those axes. So you have y square plus v square dm, x square plus v square dm, x square plus y square dm. The terms on the diagonal are the moments of inertias, and the term on the off diagonal are product of inertias. So jx, jy, jz are the moment of inertias, and jxy, these are called product of inertias. And this guy, which is a 3x3 matrix, is called as inertia tensor. Now, how do we find out this inertia tensor? For simple objects like a rectangular bar or maybe a cylinder, you can explicitly find out the values of inertia tensor. But if you have a complicated aircraft geometry, then what you do is you create a CAD model, and inside the CAD model, you can actually compute the properties numerically using the numerical integration techniques. Because at the end of the day, if you see, those are all the integrations. So you are taking the teeny tiny mass. So mass its location, mass its location, mass its location, and you perform that integration over the entire volume. And what you have is you get this mass moment of inertia. And please understand, this angular momentum is product of mass moment of inertia and angular velocity. So you have mass moment of inertia and angular velocity. Any questions on mass moment of inertia? If you look at robotics 1, we discussed mass moment of inertia in significant detail when we actually perform the robot arm simulations. So mass moment of inertia has 9 components, but if you consider the axes located at the CG, and if those axes are principal axis, then basically the off diagonal terms, they'll go to 0. So you will only have the terms in the diagonal, and that is called principal moments of inertia.
So angular velocity is calculated with respect to which plane?
So angular velocity is right now calculated within the body frame.
V slash I is written, what does it mean?
Hmm?
V slash I is written, what does it mean?
So basically, the way he's saying is the body frame orientation with respect to inertia frame. That's what he's saying. But omega is his convention is slightly different. But at the end, all the equations will be calculated in the body frame, because that is where our angular velocities are, that is where our linear velocities are, that is where our forces are, that is where our moments are going to be. So everything that you see here, that will be in the body frame. Does it make sense? Okay. So next thing is I'm going to expand this equation. So remember, this is the derivative of magnitude. This is the derivative of direction. Derivative of magnitude, derivative of direction. So since we are assuming the aircraft geometry, mass properties are not changing, and aircraft is not losing any mass, you can actually take the J out, and then you can write down the expression something like this. So the angular momentum is J multiplied by the mass moment of inertia multiplied by the omega. Since J is not changing, you can take the J outside, and now you have just the rate of change of angular velocity. And now what you have here is you have the torques or moments and you again, this is a vector equation. This has 3 components, i's, j's, and k's. Just like the linear velocity translational equation, we have the vector equation in the angular coordinates, And what I'm doing is I'm trying to get this derivative here. So please note this MB, the torques stay over here, and this guy becomes negative, and then I take the J inverse, which is the inertia matrix inverse, and multiply it on the left and right hand side. So please understand what has happened here. So MB are the external moments or torques. Step one, take this product omega B with respect to B cross J omega B onto the left hand side, onto the right hand side. So now you have a negative sign, and then take the inverse of J, multiply it on the left hand side and on the right hand side, and now you have an expression for angular accelerations is equal to inverse of mass moment of inertia and these terms. So let's define for a second. We are in the body frame. In the body frame, the angular velocities are P, Q, R. And the angular accelerations are going to be P dot, Q dot, and R dot. Everyone understood this? We are working in the body frame. In the body frame, we have U, V, W, and then we have P, Q, and R. So the derivative of omega is P dot, Q dot, R dot. And this is actually a vector equation. So if I want to write this down, I can write this down something like P dot I plus Q dot J plus R dot K. If I want to express that as a row vector, this is how I would write this down. If I want to express that as a column vector, I would just express it like this. And next step is, if you look at the aircraft, please try to understand. If you look at the aircraft, let me draw an aircraft. And this aircraft is symmetric about IB KB plane. So please understand, this is the IB KB plane. So this is IB and KB plane. So this aircraft is fairly symmetric about sagittal plane. This aircraft is pretty symmetric about the sagittal plane. So as you can see, the only products that remain are XZ on the off diagonal. So all other terms become zero. Everyone understood this? Since the aircraft is symmetric about sagittal plane, all the terms that you see in the inertia matrix, they become zero except the XZ term. So this term over here. And the reason this term remains because this is the plane of symmetry. That's why this term remains. All the terms get cancelled. Instead of an aircraft, it would have been a saucer or UFO. Then this term would also vanish, and you will only get the terms at the diagonal. Everyone understood this? Since this aircraft is symmetric in sagittal plane, you just get first row third column and third row first column term. If this would have been a sphere or a saucer, then all the terms, all the off diagonal terms will be zero. You will only have the terms in the diagonal. Everyone understood this? And the reason I'm saying this is no matter what type of aircraft it is, you will follow the exact same pattern, exact same equation. The only thing that will change is the this inertia tensor will be different for each aircraft. If you want to apply these equations to a V plane or flying wing or a quadcopter or a missile, the only thing that is going to be different is going to be this J matrix. And then remember, we have this J inverse. This J inverse of a matrix is defined as an adjoint divided by determinant. That is the definition of inverse. So what I do is, everyone knows how to find adjoint? Use MATLAB. So basically, you take the adjoint is basically you have to do the cofactors. So for an example, scratch this term, and then basically what you are left with. So you get jy, jz. This term stays over here. Then go here and then look at the remaining term jx, jz, jxz, jxz. So you get cancelled. And then depending upon whether you are in first row, first column, first row, second column, you have minus 1 to the power summation of the rows and column numbers. If you took linear algebra in undergrad, probably they taught you how to do matrix inverse by hand. For 3 by 3, it's not fun, by the way. So at the end, what you have is you have this adjoint matrix, and then you have this determinant. Please understand that jy is present everywhere. So what I did, I divided everything by jy, and then I have this guy, which is, so this is the short form expression for J inverse. This is my J inverse. And in the next part, what I do is, and this is the killer, okay? We talked about the cross products when we had vector as a row vector. Remember, we talked about the cross product when we had the vector that is expressed as a row vector. Everyone remembers the cross product that I showed last class? The vectors were represented as row vectors. If you want to do a cross product when the vectors are represented as column vectors, that is the equation, A and B. So what this means is A is given, this is very important, A is given as A1I plus A2J plus A3K, and B is given as B1I plus B2J plus B3K. And if I say A cross B, then I need to have these terms crossing with these terms. Then I will have to use the circle of vectors and then basically find out the cross product terms. Everyone understood this? If I express this vector, A vector, as a column vector, A1, A2, A3, and B as B1, B2, B3, the cross product formula is this. This is A cross B. And cross product is non-commutative. Order is very important. So that's why what I need to do is I need to take that column vector A and write that in that matrix form where the diagonal terms will be 0 and you are going to get off diagonal terms on the side. Everyone understood this? At the end, your answer is going to be the same. So if you perform cross product using the equation that I have shown here and use circle of vectors, or if you use that formula and use the cross product using the column vectors, at the end, your equation, the answer is going to be the same. Everyone understood this? Same jugglery again. So now I'm going to substitute the value of J inverse, value of omega, value of this guy, and value of this guy. And as you can see, this cross product is in the column vector. So this cross product is performed in the column vector form, and that's why I have this term multiplied by this term. And once you perform, and again, I don't know what is simple or difficult, but if you are going to use MATLAB, this is very easy because it is the matrix multiplication. MATLAB can do that in a jiffy. But if you are going to use a symbolic software like Mathematica or Maple, that cross product is helpful because it can perform the symbolic computation easily. And then at the end, all said and done, you get this equation. Are you with me so far? Everyone understood this? Okay, so here is the grand finale. The grand finale is we have equation for kinematics. We have equation for kinematics. And we have the equation for translational dynamics. And we have the equation for rotational dynamics. So as you can see, this is the velocity, linear velocity. And this is the angular velocity. These are the 12 equations. These 12 equations would remain same whether you are studying the flying saucer, missile, spacecraft, V-plane, Osprey, quadcopter, whatever you do, the equations are going to remain the same, except these tau 1, tau 2, tau 3, tau 4, those values that are dependent on J will only change. And the way you do it is, it's very standardized. For a given plane, there will be a thick, big book. You open that book and get all the parameters from the data book. If you look at our textbook, at the back of the textbook, they have given the parameters for the Zagi, which is a fixed a flying wing plane, and Aerosonde, which is again a flying wing plane. So basically, these are the 12 equations that we have to integrate to find out the aircraft dynamics. Please understand, it is extremely important to know. These equations comprise of product terms, velocity multiplied by angular velocity, sine multiplied by cosine, sine multiplied by tan, p multiplied by q. So these equations are nonlinear equations. You cannot solve these nonlinear equations by hand. You have to use MATLAB or some other numerical solver. Everyone understood this? On Thursday, I'm going to take these equations. I'm going to numerically integrate these equations and then feed the solutions of these equations to the aircraft model. Next part, any questions before I go to the next part, and which is actually quite important? So wake up, wake up. Yeah.
Shouldn't we have involved quaternion while
Baby step at a time. Let me first explain what the quaternions are. Then we will change those equations to incorporate quaternions, and then we will do the quaternion integration. Happy? Okay. So since you asked quaternion, so tell me a simple definition of quaternion. What is a quaternion?
Well, Hamiltonian was under a bridge when we derived that.
So your answer is like this. Okay. I come to Asia Poly. Where is library? Opposite student union. Where is student union? Opposite library. But where are these two? Opposite each other. Perfectly valid answer. So Lord Hamilton was under the bridge and then he found out that at quaternion and wrote, that's okay. That is the story. So quaternion, let me tell you. Physics, from physics point of view, all of you know what a quaternion is. So let's start with a simple rotation matrices. Remember the rotation matrices that we talked about in the first robotics class and in this class? And we said, let's consider the rotation about z-axis. Let's consider the rotation about z-axis. And what this rotation yielded is a different coordinate frame. Do you agree with me? But at bare bones, what was it? This was an angular rotation about an axis. Do you agree with me? Since I have a coordinate frames, as you can see, this is my I, J, and K. I could have very well said that this is the rotation theta z about K. So this is the rotation theta z about K, which means Now I'm representing rotation as a rotation about an axis. Now, if I want to express the rotation about an axis, I need four quantities. Why? Because I have I, J, and K. So if I want to express K, this is going to be 0I, 0J plus J plus 1K. And along with that, I need to express the rotation, theta Z. Do you agree with me? So what I need is four quantities. I need four quantities to describe the rotation. First, first quantity E naught is indicative of the angular rotation, and E1, E2, E3, they show you where the axis is. It turns out that this concept is so general that if I have rotation about X, rotation about Y, rotation about Z, all these three rotations can be combined into one single rotation about an arbitrary axis. So what has happened? So you have these, say, rotation about X, rotation about Y, rotation about Z. These three rotations give you a final rotation, right? So Coutonian says, or the axis angle theory says that these multiple rotation can be seen as a single rotation about an arbitrary axis. So what we have done in the past, this concept generalizes to different rotations applied together. So Coutonian is the axis angle representation of the rotation. From physics point of view, this is what it means. But then the question is, we work in three-dimensional coordinate systems. As soon as we make it fourth dimension, we cannot plot it. So that's why it is called as the hyperplane. Plane, hyperplane. Hyperplane is we visualize in mind. We cannot draw it. The trick here is, those are all unit Coutonians, which means at the end of the day, you have to have the total magnitude is equal to 1. And this is how a Coutonian is represented. So you have the Coutonians, the magnitude, which is the rotation, and then you have the axis, and then that is how the Coutonian is represented. And then these representations are equivalent. You can go to rotation matrices, to Coutonian, Coutonians to Euler angles. It's all super simple. And we'll talk about this on Thursday. And then I will show you the 12 equations that we derived. How can we write those 12 equations in terms of Coutonians, so that those equations will be free from Gimbel law. Okay, I'm going to stop here and I will continue on Thursday.